Welcome to qnawire.
So this one is slightly more involved problem. So you have a stone that is raised up to a certain height here, and at the base of a tree, so this would be a tree, there's a cannonball here, and that cannonball is sitting on the edge of a cliff. So they tell you that they raised this stone by 1.8 meters, and that this is mass M, and this stone is 80 kilograms, and this cliff here is a height of 36 meters. And I think as far as all the information in the problem, this is all you're given. So now the first thing they want you to do is come up with an expression for the final velocity of this mass here. So here's how we can do that. So essentially, we know we have a scenario where this thing swings down and a collision, or an elastic collision happens here, and then both bodies probably move forward with a certain velocity going forward, and then this cannonball here follows a projectile path all the way to some range here R. That might depend on some of the things that you're given. So the ultimate goal is to come up with expressions for this range R here. So the first thing we need to do is find out what the velocities are going to be. So the first thing we need to take note of is that this is going to be an energy problem, right? Because you have potential energy converted into kinetic energy right before the collision. So we want to say that Pi is equal to Pf to find the final velocity that it launches off the cliff here. But to get Pi now, we know that this thing is the only thing that's moving. So essentially for Pi, it's going to be the kinetic energy of this moving rock here is going to be equal to the mass of the rock times gravity times h, which is, so this is the potential energy of the rock has up here, and then it converts all of it to kinetic energy. So that would be half mv rock squared. So that this would be the velocity of the rock right before the collision. So notice the mass is common. So the velocity of the rock before the collision is just the square root of 2gh here. So essentially, now you can write out some equations for the initial momentum of the system. So you know that the rock is moving with velocity Ri, and this mass is not moving. So it has velocity 0. That should be equal to the mass of the rock times some final velocity of the rock here, plus the mass of the cannonball times some final velocity of the cannonball here. So this is your conservation of momentum equation. So since you have two unknowns in this case, so essentially that comes out to be three unknowns because you don't know the mass either. You can write expressions for the kinetic energy. So again, we said that the kinetic energy before the collision is just the rock that's moving. So this is going to be half m rock vr I squared is equal to, again, the kinetic energy after the collision, mr vrf squared plus half m of the cannonball v of the cannonball final squared. So now you have the two equations that can help you solve for the velocities in terms of this m, because you can leave it just with m because you're actually given that the mass is m. So you can go ahead and solve these two equations, but the simplest way is to just write out the equations for the velocities for an elastic collision. So you know that, so I think in the chapter you were given those momentum equations. But essentially what they come up to is that whenever you have an elastic collision, V1 final is always going to be m1 minus m2 over m1 plus m2 v1. So this is only for collisions where essentially v2 is equal to 0. So v2i is equal to 0. So this is the special case where one of the bodies is not moving. So then v2f in this case just becomes 2m1 over m1 plus m2 times v1. So notice that once, if you write out all the expressions for this v1 and v2f, you will notice that you'll get rid of some of those expressions that involve v2i because v2i is 0. So you have these two expressions for the velocity. But we're not worried about the velocity of the rock here because they're not asking anything about that. So we are going to focus solely on this term here. So this v2f is what I called vcf in this case. So since, again, this is the only velocity that we're going to worry about, let's just call that v. And that is equal to 2 times the mass 1, and mass 1 is just the rock, so that's 80, over m1, which is the mass of the rock, plus m2, which is the mass that you're given, the mass of this cannonball here. And that is multiplied by v1. But v1, we've already figured out that v1, which is vr, is the square root of 2gh. So here, this is the square root of 2gh up here. So that this expression gives you the velocity in terms of the mass. So you can go ahead and simplify this if you want. But for the meantime, let's leave it as this because we want to be able to argue symbolically in the next problem. So we're going to leave it as this, or if you want, you can just go ahead and just write this as 160 here. So this is the expression for the velocity of this thing as it leaves the cliff over here. So now for the range calculation, let's call that B. For the range calculation, you want to essentially look at these types of motion independently. So you have vertical motion, then you have horizontal motion. So for the horizontal motion, you know there's no acceleration here. So Vx times t should be equal to the total range that you have here because there's no acceleration in x. This thing just flies off here with the constant velocity in x direction. But Vy has some acceleration here. So in that case, we want to write expressions that might be able to give us this Vy or r in terms of some change in the velocity here. So you know that there's acceleration in the y direction now. So the distance that you travel in the y is Vy initial t plus half gt squared here. So you notice that in the y, again, the initial velocity is 0. So that's 0 because this thing, it doesn't move in the y direction initially. So we know what delta y is because we are given that's 36. So this is 36 is equal to half gt squared. So now we have an expression that involves t. So we have this equation that also has a t that we're not given in the problem. So let's just go ahead and eliminate t to find r. So in this case, now you have r is equal to vx times t. But t is actually, so this becomes now 36 times 2. So this is 36 times 2 over g square root, that's equal to t. So this is now vx times the square root of 36 times 2 over g. So this is all under the square root. So this gives you the range. But you know that this Vx initial is this whole expression up here. So we can say now that R is actually equal to 160 over 80 plus m square root of 2gh multiplied by the square root of 36 times 2 over g here. So notice now that you have an expression for this range in terms of only m, because everything else you have h is the 1.8 that you had here, the h initially. And you can go ahead and calculate this g for all the symbols, so you can find the range. So one thing they ask you is in part C, so what is the maximum possible range? So the maximum possible range here is given by this expression, but to find the absolute maximum distance you can travel, notice that this denominator has to be the smallest possible to make this range as high as possible. So essentially, if you could get to zero mass, then that would be your maximum range for the cannonball. So then essentially, the question asks you what value of m does that correspond to? So the maximum range corresponds to essentially a massless cannonball that's going off that cliff. And then the next thing they ask you is, so for the whole system, so the stone, cannonball, earth system, is mechanical energy conserved throughout this process? And the answer is yes, because one, you don't have anything doing work on the system. So if you involve the earth as part of your system, then the force of gravity is internal to the system. So since you don't have any external work being done on the system, then all your mechanical energy has to be conserved in that system as well. So then the next thing they ask you now is, show that your range does not depend on the gravitational acceleration. So in this case, we already have an expression for the range, but notice that I can write it like this, right? So I can write it 160 over 80 plus m. And I know that I can separate those, so I can just say square root of 36 times 2 square root of 2 times h, and then now I have the square root of g over the square root of g in this expression here, and that goes away. So no matter where you solve this problem, it's not the value of the acceleration due to gravity here is not going to affect your problem, because they are going to cancel in your final solution for the range. So again, the range does not depend on the gravitational acceleration. And that's possibly due to the fact that the gravitational acceleration here is involved in getting you initially the amount of energy that you have for the collision. So if you have a higher gravitational energy, you have a higher velocity you have a higher momentum initially, but then that momentum gives you the kinetic energy that you are going to, again, change all the way back to some kind of potential energy, and then kinetic energy as this thing falls. So essentially, the range depends on your speed after the collision, and the speed after the collision depends on the speed before the collision, which in turn depends on the potential energy that you had initially. So all of that dependence will essentially make sure that the gravity does not play a role, because they essentially cancel out at the end. So that should be the solution for this. And then you notice that if they actually want you to calculate the value for the maximum range, all you have to do is set m is equal to 0. So R max here is actually going to be 160 over 80 This is now multiplied by the square root of 36 times 2 times the square root of 2 times 1.8, which was the original height. And if you go ahead and compute all of this, you find that your maximum range is actually just 32.2 meters. And that range is only possible when m is equal to 0. So this m is for the units, this is for the mass. And that should give you all the answers that you need for this problem.